be easier. Small changes. All right, so chapter 22 practice quiz. You'll need out a student's T-table, which is in the back of the book, which I had put, I found a PDF link online as well, the same kind of table, a little bit different set of numbers, but it's all the same stuff. So a student's T-table, you'll need this, which is in the back of the book, but also put a link for this PDF, okay? It's like your D-table, but it's your student's T-table. I believe your student's T-table in the book only has this column, that column. I think those 3 columns maybe. Okay. Anywho, this chapter was all about the same kind of stuff we're doing hypothesis tests and stuff like that, but it's with smaller sample sizes. So in that case, you got to make some small adjustments. So let's begin. A professor at a large university believes that students take an average of 15 credit hours per term. Okay, that might be important. A random sample of 24 students in our class of 250 students reported the following number of credit hours they were taking. So I see a number 24 and 250. 24 seems like the actual sample size, right? N equals 24. So I think the number 250 is supposed to be, okay, 24 to 250 is less than 10% of what she was studying. So that, helps with the independent and random conditions. Okay, it's all about, all those fun conditions. So all these numbers here represent how many credit hours a student is taking. So one student said 12, one student said 13, 2 said 14, 3 said 15, so on and so forth. So I'm going to take a moment and I'm going to find the average of all those numbers. Okay, so give me a second and I'll type this in. Okay, so 12. Remember, to find the average of something, you add up all the numbers and divide by how many you have. So let's do this. 12 plus 13, whoa, plus 14 plus 14. Okay. Good, let's see here. Okay, looks good to me. Hit enter. And I got 399. Okay. And there is 2, 4, 6, 8, 10, 12, 24, right? 24 students. So divide that by 24. Whoa. It was 399 divided by 24. So before I forget, just the sum of my values divided by my number, right? And the sum was 399 divided by 24. And we get 16.625. That is my observed average, right? How do you find the average? Add up what you got, divide by how many there were. That's your average. So what kind of information do we need? Okay, remember, the only thing that really changes with a small sample size is when we go to like the Z-table type stuff. So everything else is pretty much the same. Just go into that Z-table, we now go to the T-table, okay? And what else? Okay, so we know we're gonna have to do this whole chapter is about the student's T-test, and so we're gonna need the degrees of freedom. And degrees of freedom, DF, is simply one taken away from your sample size. So degrees of freedom we're gonna need is 23. All right, so test an appropriate hypothesis. So hypothesis, let's do the H naught, H alternative, okay? He wants to know something about an average of 15 credit hours. The null hypothesis would be our p-value is equal to 15 credits, okay? And then this says taking more. So that's kind of the question, so greater than. So we're gonna do is p is greater than 15. Okay. So we got an average of 16.6. She wants to know, she thinks the average is 15, but in that sample that we got 16.6, is that enough evidence to be convincing that all of our 250 students have an average above 15 credits? So we want to know if that number from that sample is enough to say all the kids on average are going to be over 15. Do we have the evidence, or do we need to do another sample? So we have this. We got to find our standard deviation, right? So we have our n is 24, our mean is 16.625, our sigma, or we're going to say our standard deviation, okay, of our average. That's going to be, now I'm blanking for half a second. That's your standard deviation divided by the square root of your sample size, but we don't have the standard deviation of those values. So we can do it the old-fashioned way, which I really don't want to do, or we can do it by a standard deviation calculator. I just kind of realized that usually when we do this test, you guys have your the calculators here in the classroom, okay? And we don't quite have that. So let's see. It's a sample. All right. So we're going to do 12, 13, 14. Oops. Now I'm kind of like got myself. Sorry, guys. I'm like, wait a minute. I actually do what I think I did. Oh my gosh, why am I being silly? All right. Yeah, standard deviation is a standard deviation divided by the square root of your n. All right. Okay. So we can find our standard deviation, right, by just simply plugging it into a calculator. Okay, so we're going to do that, finish that up right now. I was like, for some reason, I kind of doubted myself that I was like, is that really the process? And it is the process. So 17, 17, 17, 18, 18, 18, 18, 19, 19, 19, 20, 21. All right. So calculating that, we get 2.2265 something, something, something. So I'm going to go ahead and over here and call this my S for standard deviation. Okay. And I will call that, yeah, see, there's the mean 16.625. The variance is 4.94, but the standard deviation is 2.22 something. So 2.22, let's call it 223. Let's do that. So our standard deviation of x, once again, will be our standard deviation divided for one thing, right? The standard deviation for one thing. That's what that standard deviation is for. Okay, our average student, if we do one student out of the whole population, we would expect them to have around 16.5 plus or minus, 2.5 or 5. So pretty much, within 11 to 21 credits, which pretty much covers everybody in here. Okay, that's what that says, because most students should be within there. So we want to know, though, for the entire group, if you find the average of all 250 students, right, or the average of the 24 students. If you took 24 students again, what would their average be? And it should be close to 16.5 again. Okay, it should be. And you can tell that by doing the standard deviation divided by the square root of the sample size. So 2.223 divided by the square root of 24. So when I do that, okay, clear this. I say 2.223 divided by the square root, where's the radical? Square root 24. So I get 0.45376, so 0.453, let's just call that 8, we'll round that up to 8. Okay, so that's my standard deviation. Or I'm sorry, this is my standard error, not standard deviation. Standard error is of a sample, standard deviation is just a little bit different. It's the same thing, it's just a different little name for this case, okay? So now that we have our standard error, we have our average from this, we have our average, or the number that we think it is. So with these three numbers, the 15, okay, that will be our mu, right? This will be our X bar. And so so to get our T value, okay, kind of like our T score, our Z score, our T score, okay, that T value, that's going to be our X bar, take away the mu, divided by the standard error of our average, okay? So what we get for our X bar was 16.625, take away our 15 credits, divide that by the standard deviation of standard error for 0.4538. What the heck does that give us here? We're getting close to our answer. We got 16.625, take away 15, divide that by that standard error. We get a 3.58, let's call that 1. Okay, so 3.581 is our T score. Okay, remember we'd go to our Z table when we have a Z score. We got our T value. Go to the T table. But let's see, are we doing left side shaded, right side shaded, both sides shaded? What are we doing? The question here says greater than, okay? So if our average is supposed to be 15 that we're comparing it against, that's the middle of our normal curve, okay? If I go out, how far out do I go? Well, that's my standard error. Okay, my standard error is 0.4538. So this would be roughly about 15.5, roughly, okay? This would be about 16. That'd be about 16.5. That'd be about 17. So what I got for an average was 16.625. So this is not perfect because I rounded that number, but it's going to be somewhere about there is that average of the group. Okay, this was my mu. So if I'd make a basic looking normal curve, you should see that it's a tiny little number over here. There's not a lot of space over there. Okay, because you see it's greater than. This is greater than the right side. So I'm finding the probability of having a T-score with degree of freedom of 23, okay, that is greater than 3.581. So what probability would give us that is greater than that little T-score? All right, T-table. So once you get your T-score, look at a T-table. You got to know left side shaded, right side shaded, and it can be helpful to draw a picture. Okay, so on this table, we're going to start by looking for our degree of freedom of 23, which I see right here. So what we're kind of looking for is something along this line of 23. Okay. So that's going to help us out right here. Now, if it helps to remember, right, that says degree of freedom up top there. And then you see how we're only shading the one side? If I was doing, if this said not equal to, I would go over here to the reflection, to like the negative 3.5, and I would be looking at the left side shaded and the right side shaded of the positive. Both sides would be shaded if it was not equal to. Ours isn't like that. Okay, it's just the greater than. So we're going to look at the one tail number, and one of these numbers is going to be our approximate answer. Okay. Okay. So now we got to find where this matches up. So what I mean by that is look at your our t value, right, the t-score of 3.581, so about 3.5, 3.6. Can we find that number on this table? And I'm looking down here, 3.56 or something like that. And the closest I can get is right here in between these numbers here. In fact, it looks pretty good, like it's right there in the middle of that. So that means my answer will be in the middle of these numbers. So it's going to be less than 0.001, but greater than 0.0005. So I'm going to kind of like imagine that for a moment. I've got 3 digits. Let's make that 4 digits. That's 4 digits. So that's kind of like 10. That's kind of like 5. So we would estimate the number to be about 0.00, like 07, 08, somewhere in there. Okay, we know it's less than this number, greater than that number, because our t-score was greater than this, but less than this. It's in between there. Okay, it's in between those numbers, so it's got to be in between those numbers. Okay. All right. Let's say so we know the probability is less than 0.1%. Okay. But we know it's greater than 0.005. Okay. I'll make a little note here that the number is not too small, but it's still a small number. Okay. And that's where you can actually, they have the calculators, you can find the exact number. But for right now, all I want you guys to be able to do is look at this table and know how to read it. So the general flow of this, right, is to do this, is to go down from your degree of freedom. Okay, so you start here. Okay, work your way down. Okay, step 2 is to then go across to try to find the number of your t-score. Okay, and ours was in between those 2 numbers. So when we found that, we then, for step 3, okay, then went up to the line that was for our problem. So ours was just the greater than, the one side shaded, it was there. How do we get the degree of freedom again? All it is 1 take away your sample size, or 1 taken away from your sample size. So it was 23 because our sample size was 24 students. So our degree of freedom is 23. Why do they say n minus 1 is the degree of freedom, and why do they even take away 1? Great question. They have their reasons. I'm honestly not quite sure why it's take away 1. It's just the thing that they decided was the best for the equation. All right, so we got the number. We know it's between 0.001 and 0.0005. And Cassidy, I'll answer your question after I finish going through this. All right, kiddo? So I got this for an answer. Test an appropriate hypothesis and state your conclusion. So we have not stated a conclusion yet. We got our probability, but we didn't make some sort of decision yet. The decision would be, do we reject the null hypothesis, or do we fail to reject the null hypothesis? So remember, when it says state your conclusion, that means we're going to say reject the null hypothesis, or we would say fail to reject the null hypothesis. So remember the general guidelines, okay? Think about 0.05, okay? Like 1 out of 20, 5%. Okay, 5% chance of something happening. If it's less than 5% chance of something happening, we generally reject the null hypothesis, okay? Generally speaking, right? For that one there, it has to be less than 5%, less than 0.05. For this one, that's anything that's greater than or equal to 0.05. That's a general rule, Okay, it's not set in stone. It's not like it's written down as like this is how it always is. There's a lot of debate about that number in general. However, it's always been used, I guess, for a number of years as a general standard of like, for most problems, okay, that if you want to reject or fail to reject the null hypothesis, that little line in the sand is 5%, 0.05. So 0.001. So at the highest, even without getting the specific number, we know it's between those numbers, just on the information we were given. So we're going to go ahead and say, since it's less than this, okay, this is like what's happening. So we are going to reject the null hypothesis. We should reject the null hypothesis. So what does that mean in plain English? Okay, if you reject the null hypothesis, that means that the alternative hypothesis is pretty much, you're assuming it's true, right? If you're getting rid of one option, the other option, if there's only two options, the other option is true. That means the actual average of her students is not 15 credits, but it's actually higher than 15 credits. Yes, the sample was 16 and a half. So that's one obvious, like, well, yeah, we took a sample and it was more than 15. But you understand if you took a different sample, it might be less than 15. If you took another sample, it might be 18, it might be 15. You don't know. We just took one sample. But according to what we just calculated, that one sample has a very, very, very small chance that the actual average is still 15. Okay, it's got a less than 0.001 chance, okay, or less than 0.1% chance, okay, of getting these results if it really is 15 credits. It might be just a very rare chance. We don't know the other 226 students' data, okay? But just from the sample, we should reject the null hypothesis. We should reject that they're equal. All right, this last one I think is probably a lot easier. We've already done all the calculations. So 95% confidence interval. Okay. So if you remember, we always use that Z star number, and that was always 1.96. So remember, traditionally, Z star, we always use 1.96. That was with a regular group. Okay. So will that change when you're doing this stuff? Okay, will this number change when we're doing these numbers? Okay, so what we have to do with this table, again, this is now for number, this is for, okay, let me grab, I've got another one of these sheets. Let me grab this so I can write on it. All right, so you can obviously use the same one, and you can see confidence level 95% on there. But what does that mean? Okay, what the heck does that actually mean? We see a 95% confidence level. That's what kind of matches up with the numbers. If you look right above, you see the 1.96. That's what we usually use. That's for our Z-score. Okay. So are we still going to use 1.96? Okay, we have to adjust it. Okay, as you notice for the sample, the degree of freedom of 1,000, it's really close to 1.96. The bigger your population, the closer it is to the numbers of the Z table. Okay, the smaller your sample, because the smaller your degrees of freedom, as you notice, these numbers drift away. Okay, you notice this 1.96 for 95% confidence level. If you've only got, let's say, a sample of 2, which means degree of freedom of 1, you should use instead for your Z star, you should use 12.7. Okay, what that does, it just increases your interval. Okay, because you have such a small sample, you're supposed to basically say, we're not really quite sure. We're just going to open up this interval to a larger number to account for the possibility that we're not really sure if we're even close to the actual average. Okay, this is where a lot of errors can come in, right? Where you have a lot of mistakes can happen because you have a small sample. So they say, you know what, we're just going to Smaller the sample, the bigger the window, the bigger the interval, okay, when you have just a smaller sample, okay? You can't do that with normal Z tables. That's why somebody had developed this T table, okay? So what we're going to do is match once again our degree of freedom, which is 23. And we're going to go up from that 95% and use that as our Z star number, okay? So we started here, okay? We went here and found that. And then step 2 was to then go on to where we see the number there, okay? And that number is 2.069. We're going to use that for our Z star, okay? 2.069. So we're not going to use that. We're going to use 2.069. So that equation, okay, for the confidence interval was going to be we start with our average, which is 16.625. And we're going to do the plus minus of our Z star, which was 1.96, but now it's going to be 2.069, okay? By making this number a little bit bigger than 1.96, now it's a little bit bigger, that's good. When we multiply that by our standard error, okay, sorry, our standard deviation, that's going to kind of open it up so that we have a better picture. All right. So, and we want to use not our standard deviation here of the one thing. We want to use the one for the group. We want to know about the bigger group, okay? So, looking at my standard error, I got 0.4538, okay? So when I multiply all that stuff together, I should get an interval. In that interval, I should capture the true average. So 16.62 is probably not the true average of all 250 students, but it should be close. How close? Plus or minus this close, okay? So I'm going to do this. I'm going to subtract it, and then I'm going to add it. That way I get a low number and a high number, okay? So let's take a quick second and let's calculate this. I got 16.625 minus 2.069 being multiplied by 0.4538. This calculator should use order of operations, and it does. I get 15.686. Let's just do the 3 decimal places. And then let's do the right side. So we'll say 16.625 plus 2.069. You multiply by 0.4538. You get 17.564 around. Okay. So, interval, but it says to interpret my interval. Okay. I mean, put it into plain English. Okay. Make it so it's easy to understand and not just be a mathematical set of symbols. Okay. Or a set of mathematical symbols, I should say. So this basically says, and I'm going to write this out in words in a moment, but this says I have 250 students. Okay. Out of those 250 students, I sampled 24, and I got an average of 16.625 credits. Okay. And the actual amount of all 250 students, okay, I know 16.6 is probably not the perfect true average, but I think I'm close. And I'm like 95% confident that it's between these two numbers. Okay. What I mean by 95% confident is if I did this test 100 times, 95 out of those 100 times should capture the real amount somewhere around these numbers. Okay. So I'm going to say interpret your interval. Whoops. The true, not percent, the true mean credit hours of the students is between those numbers. The true mean credit hours of the students is between 15.686 and 17.564 with 95% confidence. And I throw that in there to make sure they know that we used a 95% confidence interval. Okay. So with this quiz, with this assessment, 2 questions. The first one is reject the null hypothesis or fail to reject the null hypothesis is going to be your answer. And all that work is just the proof to get there. For the second question, okay, the true mean credit hours of the students is between 15.686 and 17.564 with 95% confidence. That's the answer. And this stuff up here, we did this calculation was the work. Okay, so to review, let's kind of just go from the top, just do a quick talk down through the whole problem again. So for this first problem, a professor at a large university believes that the students take an average of 15 credit hours per term. That's our mu. That's like the perfect average we're kind of looking for. A random sample of 24 students in her class of 250 students reported the following number of credit hours they were taking. So 24 students is the sample size, 250 is just information so that you understand that she doesn't just have like 50 students or 1 billion students. She's got 250. So that's supposed to help you with the, determining if we can use, this kind of data and stuff. So if it's too big of a sample, they say it's not that good. If it's too small of a sample, it's not that good. You want a Goldilocks. You want it less than 10% of all of them, but you kind of want more than just hopefully a handful, right? That's kind of the dream. But 24, and obviously this is kind of a small number. This is why we're going to use the student's T table instead of the normal Z table, okay? Because it's a small sample size, but that's the whole chapter's about. They give us the data. That's the raw data. So they want us to find the average and the standard deviation. Okay, average, add them up, divide by how many you got. That's your average, simple average. And we got 16.625 is that number. Added them all up, divide by how many we have. For our standard deviation, okay, that's calculator work. What you're supposed to do is essentially find the average, take each number, say like 12 minus this number, square that number, okay, and then do that for all of these numbers. Take each one of these numbers, subtract it from the average, square that number, and then you add all of those values up, and then you divide that by, you should be dividing that by 23, and then you square root that number, and that's how we get 2.223. It's a little confusing. That's why we've never really done it by hand. That's why we just use a calculator. It can get kind of complex and take a little bit to get that answer. So we got 2.23 is the standard deviation. It's a standard deviation just for one number. Okay, it's just for one of these numbers. So if you get one more student to throw in the mix, we would expect them to be 16.625 plus or minus about this number, right? 1 or 2 times of these numbers. So that gives us our standard deviation. We have our mean. We've got our sample size. Our degree of freedom is just one taken away from our sample size. They say the question is something about, make a hypothesis, state your conclusion. The hypothesis would be that we would expect it, we're testing against 15. No hypothesis is the professor's right, it's 15 credits. The alternative is it's more. How do I know it's more? Because it said something about testing to see if the students are taking more credit hours than what the professor thought. So we got the P equals 15 or P is greater than 15. Then we find what's called our standard error. So we have a standard deviation. If we threw one student in, we would expect it to be around 16, but more room for error, right? It could be 15, 14, 13 even. It wouldn't really surprise us. If it was like, 16, 17, 18, 19, even like 20, probably still wouldn't really surprise us, but we would expect it to be closer to 16, but there wouldn't be any surprise. If we got a number like 5 or like 23 or 30, it would probably throw us off a little bit. And this standard deviation kind of tells us that it's going to be closer to 16, okay, plus or minus about 2 or 3. So to find this, the standard error is when you have the whole entire group. So we took a sample of 24 students and we took a different sample, a different random sample of 24 students at 250. Okay, we would expect it to be different than the 16.6, right? But according to these numbers, we would expect it to be not 16.6 plus or minus this 2 or whatever. It's now 16.6 plus or minus this about a half, about 0.45. Okay, we would expect the group to be, basically between like 16.1 and 17 or so. That's what this number says, is that the average of another group of 24 should have a standard deviation from the average that's around this number. Okay, now that we have that information, we can say the average that we found, take away from our mu, divide that by our standard error of the group. Okay, when we do that, we get 3.581. So the 16.625 minus 15 divided by that gave us that. So now we have our t-score. This is usually we have a z-score. Usually we go to the z table. We're going to go to a t table. Okay, that's where we kind of went down the degree of freedom, 23, went over until we found our number, or at least close to it. Okay, and it would be somewhere about between those numbers there. Okay. So because it's less than 0.001, greater than 0.0005, since we're going to use it as a general marker, okay, our alpha is 0.005, 0.05. Yeah, 5%, 1 out of 20. Okay, we're going to use that. Anything less than that number, we're going to reject the null hypothesis. If it was greater than that number or even equal to that number, we would say we just don't have the evidence. 1 out of 20 is a small chance, but it's not a crazy chance. But anything less than that, anything less than 1 out of 20, they say go ahead and reject the null hypothesis. Okay, this is a general rule. So because it's less than 0.05, we're going to reject the null hypothesis. That means we should, reject the null hypothesis. Meaning, her students have an average. We're like pretty dang sure that her students actually have an average greater than 15 credits. Okay, so that leads us to question 2 about the 95% confidence interval. That's where we look at the t-table again and find our z-star number. Okay, our z-star, remember, we used to always say 68, 95, 99.7. 1 standard deviation, 2 standard deviations, 3 standard deviations. Okay, we learned in the not too near past that we don't use 2 when we go to this confidence interval. We actually use 1.96, which is a closer number to actual 95% of what your numbers should be. Okay, 1.96. However, with a smaller sample, you've got to adjust that number. Okay, and the smaller your sample, the bigger that number is going to be. So when we get to a degree of freedom of 23, 2.069, they say should be your 95% confidence interval z-star number. Okay, 2.069. So we're going to use that, and that is multiplied to your standard error. So the average we found plus or minus the z-star number from the, being mindful of degree of freedom times our standard error, and that's going to give us these numbers here. So this is our interval. Inside this interval, we believe we've captured the actual true average of all 250 students without actually, asking or sampling every single of her 250 students. That'd be a census. We're going to do that. So without asking every single student in her classes, all 250, we're just going to say we're 95% sure that the actual average is in between these two numbers, which kind of makes sense now that why we would reject the null hypothesis, because even at the lowest end that we would imagine, it's still 15, almost 15.7. Okay, so that is, we're pretty sure that her class, all 250 students, okay, in all of her classes, their average is bigger than 15 credits. Okay, so the true mean credit hours of the students is between 15.686 and 17.564 with 95% confidence. All right, I'm going to stop the video.